Hello, today we are going to work on lesson 2.6. It's called Sit Back and Watch Your Money Grow. So I like to think how money can grow. Our quote for the day says, if I take 30 steps linearly, I get to 30. If I take 30 steps exponentially, I get to 1 billion. So we're going back to that original concepts that we learned back in 2.1 with the simple interest and the compound interest, and comparing how simple interest, the idea that simple interest taught us about a linear growth and compound interest taught us about exponential growth. And number one is asking us to describe some linears, differences here between them. So linear is repeat addition or subtraction, right? If it's a decreasing linear model. And exponential is repeat multiplication. And some pictures of what we notice that they look like, where linear could be anything like this, like any of those right directions. And now we're going to look at exponential is going to be growing like this or decay. So let's go ahead and jump in. We're on page 208. So 208 says, if most people won $15,000 on a game show, they'd go on a spending spree, but not you. You're too smart for that. Instead, you decide to invest that money to make it grow. I'm not sure how patient you are, but what if you were super patient, like patient enough to let that money grow for 40 years in a fixed rate investment? Let's take a look. Make sure that you answer every question with a complete sentence. So we have a table of the money. So this is the year we invested the money at $15,000. And 7 years later, it looks like we're going to have $24,086.72. And then they plotted those values on this graph. And this is really all we have the data through year 7, right? But it looks like if we continue to let it grow, it would be all the way up to, in 40 years, almost like 225,000. So it says, for each value in the table after the initial investment, divide the amount by the value of the account the previous year. What do you notice? So let's just write out what a few of these would be. That would be 1650 divided by the 15,000. Then 17,173.50 divided by the 1650. And then let's do another one. Let's even do 6 and 5. So 22,510.96 divided by 21,038.28. So let's go to Desmos and check it out. Check out these. So we have 16 divided by 15,000. So that's 1.07, 17, 50, 1.07. And then the other one was 22,510.96 divided by 38.80. Or 78, I think it was. 28. Looks like they're all 1.07. Number 3, let's stay right here at Desmos for a minute. Number 3 says, what does your result in question 2 say about the type of growth this account exhibits? Find the relative change. So I am going to save this as lesson 2.6. Intro to exponential. Okay. So I'm going to make a note here So number 3 says it shows repeat multiplication by 1.07 each year, so exponential growth. The number 4 says find the relative change in value for each year in the total compared to the previous year. So let's do that. I'm going to make another note here. So number 4 is relative change. So let's do relative change. So relative change, let's do 16,050 minus 15,000. That's the new minus the old divided by the old 15,000. Okay, so that comes out to be 0.07. And I'm going to put that formula up here. So new minus old divided by old. Okay. And then let's do another one. I'm going to do the last one, 2486.72 minus 22,510.96 divided by 22,510. Okay, so it looks like we have relative change of 0.07 or, and then number 5 says find the value of the account. Okay, so let's do this. So number 5 says looks like we have relative change of 0.07 or 7% increase each year. Okay. So number 5 says find the value of the account after 10 years. Don't multiply by 1.07 times. That's what exponents are for. At 1.07 10 times. So let's make a note here. So number 5 is asking us to find the account. So we learned back in the account, back in 2.1, we learned about the compound interest was, and then we said exponential. So exponential model we said was y equals a times b and then to the x, or y equals starting value times the growth factor to the time. And then we said where the growth factor is equal to 1 plus the percent, or actually 1 plus the relative change. Okay. So that means we have y. I'm going to go back to our paper for just a minute so we can see here how this will be written down. So this was exponential and finding the value after 10 years. After 10 years. So we said this was when we talked about the compound interest, it was the starting value times 1 plus your relative change to the x, which is years in this case. And 1 plus relative change is our growth factor. So we should have y equals, our starting value was the 15,000 times 1 plus 0.07. That's our relative change. So 1.07 to the x years. So let's find out what that is. And decimals. So y equals 15,000 times 1.07 to the x, and hit enter. And we could just, that's our equation. So I'm going to just, I'm going to put that down here. So here we could just do this one instance, 15,000 times 1.07 to the 10. So after 10 years, we would have $29,507.27. And then 6 says, use your answer to question 3 to write an equation in the form of, which we just showed, where the expression describes the amount of money in the account after X years, starting with the 15,000. So that's what we did. That's what we did right here. So I'm going to say this is number 6. And so I'm going to write it out just in X. Okay, so we're going to take this equation. That's number 6. And let's move to page 209. Number 7 says, verify that the equation you wrote generates the account values in the table. Ideally, you would use the table feature on either a graphing calculator. Yes, we're going to do that. So we have our equation, and you can tell it's an equation because right over here on the left, there's a color blue because it shows kind of like a graph. Now, to get the graph, we're going to hit enter, and we're going to actually have your cursor up in that equation again, and then we're going to go up to the gear. See where I have up the gear? And I'm going to, when I click on that, it gives me options now down where equation is, and I'm going to hit table, convert to a table. Now the values that it starts with are -1, -2. We're going to just, and I'm going to start with 0, 1, and then I'm going to arrow down and replace those with 2, 3, 4, 5, 6. And let's go back to our original table and just validate. After 6 years, we had $22,510.96 rounded. And now if we want to see this on a graph, remembering Desmos, we can go ahead and click the magnifying glass, and it does our scaling for us, which is awesome. Now, if you have a mouse that is a wheel on it, you can just zoom in and out with your wheel. But over here to the top right, where my mouse is right now, I'm circling, there's a plus and minus. So if I hit the plus, I'm zooming in. If I hit the minus, I'm zooming out so I can see the big picture. Okay, so let's go ahead and flip over to page 210, number 8. And we're going to use everything we've come up with here in Desmos to answer some questions. So we're on page 210, number 8. It says, for the spreadsheet displayed earlier, find the amount for the function. So we do not need this because we are not using a spreadsheet. But we can answer number 9 for the function described. So using Desmos. So using Desmos, describing the value of our 15,000 investment, find f of 12. So there's a definition here on page 209 of a function. A function is a relationship between two quantities where each input produces a unique output. So for us, our function is f of x. It's the same as y. We're just saying we're using x as our input to this function. It's like the function is kind of like our recipe. We're putting x into our recipe and what comes out is y. So our function for this scenario is this. So when I change my years, I'm multiplying by this growth factor of 1.07 and then by our original amount of 15,000. So we want to know what is f of 12 and describe what it means. So f of 12 is the value in our account after 12. So let's capitalize this. It's just going to be the value in our account. Erase the is. After 12 years is, and we have to go back to decimals to find that. And we're going to put 12 in our table. So our table will allow us to put any number we want. So 12, and there it is. After 12 years, we would have $33,782.87. So let's just put that in here. I'm going to just make a note here so you can see. So number 9 says the value in our account after 12 years is $33,782.87. Okay. Number 10 says, look back at the graph that illustrates the value of your account. Trace along the graph slowly from left to right and describe what the changing steepness of the graph tells you about how the graph is growing. So we're in our graph in decimals, and I'm just going to grab my line here. Let's see. Well, show me my points. So if I go back to this and I hit my gear again, I should be able to. Well, I'm going to go ahead and just type in the equation again without the table. Because when I have the equation typed in, I can then, and when it's just the equation, I can then just grab the graph and it will let me scroll. So here I'm tracing. Does everybody see now? I can grab and see what's going. You can see as you're moving along, it is getting large very quickly. Let me do that. So number 10 says the output Y is growing rapidly. Okay. The output Y is growing rapidly. So number 11 is our lesson check. Let's remember that. It says, how much interest will you earn from 0 to 5 years into the investment? This will be the difference in the value after 5 years and the initial investment. You could use the formula for the function, but the table of values printed earlier is a better choice. So we had year 5, so $21,038.28 minus the 15,000. So $6,038.28. Number 12 says, how much interest will you earn between years 35 and 40? This time the formula is your only option. So let's find our function at 40. And then we can subtract our function at 35 and find the difference. Let's go back to Desmos here to do that. So we can just go to our table, which is super nice, and we can find 40 and 35. So we can say 224,616.87. And then at 35, it's 160,148.72. So let's just subtract it. 224,616.87 minus 160.44. Whoops. 148.72. So it looks like between year 35 and 40, we gained $64,468.15. That is crazy. Share my paper again so you can see it. And there it is. We gained between year 35 and 40, $64,468.15. 13 says, describe what you can learn from comparing the answers to questions 11 and 12. Also describe how that fits in with your answer to question 10. So look at just between the first 5 years, we gained $6,000. And in the last 5 years, so they were both a change of 5 years, but we gained $64,468. It's crazy. And so 13, we could say both were a change in 5 years, but the longer you wait, the quicker your money grows. Awesome. And that is the end to lesson 2.6 part 1. So when you catch us back, be ready here on page 212. We're going to look at a situation or a new idea of exponential modeling, but this time you can see our numbers are going down. And this is all about a capping with coffee. So we'll catch you back for lesson 2.6 part 2 in a bit.